Autonomous driving technology is rapidly gaining popularity, offering unprecedented convenience and efficiency as a vital part of future transportation. However, the current decision-making strategies in autonomous driving are far from perfect. Conflicts often arise between autonomous and human-driven vehicles due to differences in driving strategies. Fixed autonomous driving strategies often fail to meet the diverse needs of different drivers, leading to reduced comfort and flexibility of driving. This is where EEG research plays a role. By monitoring drivers' EEG, we can capture their perceptions and cognitive responses to the environment in real time during driving. These data not only help us understand the decision-making processes of drivers, but also reveal the differences in responses among individuals when faced with the same driving situation. By integrating these research findings into autonomous driving decision-making control systems, we can develop more intelligent and adaptive technologies that reduce chaos and conflicts within the traffic system, making every journey in the future safer and more efficient. To address this, we propose a personalized driving behavior prediction framework based on EEG data, using models built from data collected in longitudinal car following experiments. This study utilizes the synchronous collection of drivers' electroencephalogram signals and driving situational data, combined with advanced DR-EEG decoding techniques and long short-term memory models, to extract key features related to driving. It constructs a personalized driving behavior prediction model that accurately predicts drivers' behavioral responses in various situations, ultimately generating personalized driving strategies to enhance the intelligence level and user experience of autonomous driving systems. We collect data using a driving simulator and an EEG cap. Physiological signals are recorded in real time during the driver's operation and matched with the driving process. Car following is the most common part of the driving process, where the rear car follows the front car and the driver generates corresponding decisions based on the stimuli from the front car. We designed 3 car following experiments, each of which recorded the space headway at a sampling rate of 60 Hz using a driving simulator, time headway, gas pedal, brake pedal, speed, acceleration, TTC, and steering wheel angle data. Current autonomous driving decision control models cannot ensure that each driver receives an experience that matches their personal driving style. Additionally, they differ from human drivers' behavior and do not integrate well into the existing traffic system. To address the mismatch between human behavior and fixed autonomous driving systems caused by driver heterogeneity, we attempt to train personalized prediction models for each driver. The prediction framework is based on the collected EEG data and driving behavior data. The EEG data first undergoes pre-processing, and the DR-EEG decoding method is used to extract the driver's EEG features, namely the TFCMI features. DR-EEG decoding is accomplished through the TFCMI method, which involves wavelet analysis, joint probability computation, and mutual information calculation to transform EEG signals into TFCMI features. EEG signals are decoded using the time-frequency co-information method, integrating multidimensional driving cognitive information across time, frequency, and spatial domains. The driving situational data, including space headway, time headway, gas pedal, brake pedal, speed, TTC, and steering wheel angle, are used to generate situational embeddings that capture the underlying features of the driving situation through a long short-term memory model. We extracted situational embeddings to capture the underlying knowledge of the dynamic and constantly evolving driving situations resulting from drivers' diverse kinematic responses to stimuli. The situational embeddings that correspond to the driving behavior data in each time interval were extracted by training the LSTM models on the dynamic driving data. These embeddings encapsulate the salient situational characteristics because the LSTM model is particularly well suited for effectively capturing the temporal dependencies in time series data. The obtained EEG features and context embedding information are used to train both general and personalized gradient-boosted regression tree prediction models with driving behavior as the target. This allows for precise prediction of personalized driving behavior, evaluated using R-squared and MAP metrics. We display an example result of the different prediction models based on varied EEG features. They are original signa, power spectral density, wavelet decomposition, empirical mode decomposition, phase-locked value, corrected amplitude envelope correlation, time-frequency cross-mutual information, The predicted spacing curve based on the TFCMI features demonstrated greater consistency with the observed spacing curve, highlighting the efficacy of this approach for predicting driving behaviors. We illustrate the distribution of importance values for the TFCMI features employed in this study. The identified vital connections varied among frequency bands, underscoring the complexity and richness of EEG information. Based on the extracted TFCMI features, well-received models such as the RBM, XGBoost, SVR, GAN, FCN, DBN, RF, and GBRT models were trained to predict different driving variables. The Prediction Accuracy Index, MAPE, and R-squared value of speed and acceleration in the 3 driving experiments are depicted. In the absence of situational embeddings, our analysis revealed that the GBRT, XGBoost, and SVR models exhibited superior performance in predicting speed and acceleration, as evidenced by their smaller MAPE values and larger R-squared coefficients. With the introduction of situational embeddings, that is, the LSTM hidden layer features mined from the time series of perceptual driving situations, the GANS, in EXP1, RBMS, in EXP2, and DBNS, in EXP2 and EXP3, models exhibit significant improvements in predictive performance. We compared the predictive performance of the individual and general driving models. They are individual model, partial general model, DG, distilled general model. We found that using individual DR-EEG decoding features and individual situational embedding for model training is an effective method of personalized acceleration prediction compared to the general driving model that trains using the information derived from all drivers' data. This research demonstrates personalized prediction of car-following driving behavior based on EEG information and situational embedding features. Results show that TFCMI effectively captures interregional brain correlations, while situational embedding improves predictive performance by 27.28%. Models integrating individual perception outperform general models. Key neural activations in the frontal and left temporal lobes highlight their roles in driving decisions. These findings demonstrate the potential of personalized brain-machine interaction and intelligent driving systems. Thank you for watching.